Hello everyone, I'm Zhonghua Zheng. It is my great honor to present our work. Today I'm going to introduce how to use machine learning to estimate and regionalize the global aerosol mixing state. I want to thank all the co-authors for their contributions. First, let's talk about aerosols. If we look electron microscopy to look deeper into aerosols, we found aerosols are not pure substance. In contrast, they are complex mixtures consisting of different species. So we use the term aerosol mixing state to describe the distribution of chemical species across a population of particles. For example, let's assume an aerosol contains six equal amount of species and six particles. The six species can be distributed into six particles in different ways. For instance, if each particle only contains one species, we call this aerosol as fully external mixture. If each particle has the same percentage composition, we call the aerosol as fully internal mixture. Between them is an intermediate mixture. We use an entropy-based diversity metric, aerosol mixing state index, to quantify aerosol mixing state. Here, 0% means fully external mixture, and 100% means fully internal mixture. Aerosol mixing state could be defined based on different purposes in different solid species. For example, if we are interested in optical property, since black carbon is absorbing and we assume other species are not absorbing, we can have black carbon as one surrogate species and non-black carbon as another surrogate species. We can also define them based on hygroscopicity. Then we can calculate the Chi-O and the Chi-H. We find between the fully external mixture and the fully internal mixture, Chi-O, Chi-H, and Chi-A, they are different. Aerosol mixing state index is important for our system. Here is an example. Particles can be activated as cloud condensation nuclei and form cloud droplets. Let's consider three populations only with a difference in aerosol mixing state. We can find that they have totally different results of CCM activation. For example, if we assume particles are fully internal mixture, six particles are activated. But if in reality, let's say particles are external mixture, we find that there's an error compared to our assumption of fully internal mixture, right? And you can see the relationship between the error and the aerosol mixing state. The model PATMC is a benchmark to study aerosol mixing state index. In order to map aerosol mixing state index, recent studies have combined the weather forecast model with PATMC to do the regional study, mainly for California. Although this approach is good, it is very computationally expensive. Therefore, for global mapping, we develop a surrogate model based on supervised learning, trained from many box simulations. Then we use a system model simulation data and our surrogate model to map, or say emulator, to map different mixing state index at a global scale for 2 seasons. Then we are interested in analyzing global patterns of aerosol mixing state index. We may want to divide them into different zones, like what we did for climate zones. We could use the clustering to regionalize the global mixing state indexes. There are two steps. First, we stack all the monthly maps together for different mixing state index. We can have 36 maps in total. You can assume that each pixel in the map is a data point with 36 dimensions. Then we do the k-means clustering for 36 dimensions. We end up with 11 clusters. We can assign each pixel to its clusters. That's about regionalization. The results are pretty nice because we never provide any spatial information like longitude or latitude, but the grid cells tend to get together. Based on the results, we can study spatial temporal pattern. Besides, we can define aerosol mixing state zones that could be useful for atmospheric science research. Thank you very much for your attention. Please feel free to let me know if you have any questions and suggestions.